Now let's solve a problem that is called as acceptance at university, and we are trying to build a model which will predict whether a particular student should get accepted at the university or not. Now this prediction is going to happen based on two criteria. One is marks scored in the entrance test, and the other one is grades that the person has scored in its college or maybe school. Okay, so let's take it school. Okay, so based on these two criteria, we will predict whether a student should get accepted at a university or not. Now we have, let's say, a student 1. This person has scored in test. This person has scored, let's say, 9 out of 10. Okay, and that person has scored in grades, that person has scored like 8 out of 10. So this person is having the entrance test scored as 9 out of 10 and grades as 8 out of 10. So tell me whether this person should get accepted at the university or not. Obviously you will say that this person should get accepted at the university. You will say that. Now let's say that there is a student called student S3, and this person has scored in test, let's say 7 out of 10. Okay, or let's keep it to more, like 3 out of 10. This person has scored in test 3 out of 10, and in grades that person has scored like, let's say, 4 out of 10. So whether this person should get accepted at the university or not. So you will definitely say that this person should not get accepted because the test and the grades are really low. Now let's say that there is a student 3, and this person has, let's say, scored 6 out of 10 in entrance test, and let's say 7 out of 10 in grades. Okay, 7 out of 10 in grades. So whether this student S3 should get accepted at the university or not. Now some people will say yes, some people will say no, but we want one solution, right? We want either to accept it or not. Okay, so that is why we will try to build a model that will be able to predict whether this student S3 should get accepted at the university or not. Now to build a model, you need some historical data. So when we ask the university that give me your historical data of the accepted and the rejected student, and that college is going to give us that data. Okay, now we got the data, and let's say we are having y-axis and the x-axis. Okay, let's say y-axis is representing grades, x-axis is representing the entrance test marks. Okay, now we are going to have some values. So let's say we are having like 1, 2, 3, okay, 4, 5, 6, 7, 8, 9, and 10. And here also 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, now the student S1 has scored like 9 and 8, right? 9 and 8. So we can go like 9 and 8. So that person is going to be coming here. Okay, and the other person has scored like what? Like 3 and 4. So we can go like here also 3 and 4. Okay, 3 and 4. And another person who was student S3, that person has scored like 7 by 6. So I'll say like 7 by 6 here. 7 by 6 here. Okay, now I want to predict whether the student should get accepted or not. So let's remove it as for now. And as I said, we got the historical data of the university, and our historical data of the university looks something like this. We are having some accepted students here. Okay, and we are having some rejected students here. Okay, so the red area represents the data point that is accepted students, and the green area represents the data point that has, red area represents the data point who are rejected students, and green area represents the data point that are accepted students. Okay, so these area is containing a lot of data points. This containing a lot of data points because obviously the university has a lot of data points, right? Okay, now based on that, tell me whether a student should get accepted or not. Whether the student S3 who is having the entrance test as 7 by 6 and 7 by 10 and grades at 6 by 10, whether this student S3 should get accepted at the university or not. How will you answer this question? You are simply going to plot these point out. But before plotting it out, we want to separate the data points, right? We want to have some kind of separation here. Okay, so here as you see that we are able to find out a very big separation, which is representing whether the student should get accepted or not. So which is representing the line here. So this line is representing the separation between them. Okay, and above this line, whenever a data point is going to come above this yellow line, I will say that the person should get accepted, and whenever the data point that is going to come below the yellow line, I'm going to say the person is going to be rejected. Now let's see for the 7,6. So 7,6 is coming around here. 7,6 is coming around here, and I can say that this person is going to accept at the university. This person is going to get accepted at the university based on the data point that we are having. Based on the line that we are having, we are able to say that the 7,6 is lying above the data line, is lying above the line. So I will say that this S3 student is going to get accepted at the university. Now the method that I'm talking about is called as logistic regression. First of all, let me tell you that the method that I'm talking about is called as logistic regression. Okay, now again, as I said in the last lecture, finding this line is whole machine learning, right? In the last lecture also we tried to find a line like this, but this problem was the example of regression problem where we are having some continuous values. But this problem is the classification problem where we are having categorical value. So here we are predicting some value here. The price of a house is a value, but here we are predicting the category, whether person is going to accept or the person is going to get rejected. Okay, so again finding this line is again the whole method of logistic regression, that is whole machine learning is. And now the question is, how do we find the line that cuts the data into two parts, as you see. Okay, how to find this line that is going to best cut the data? That is the question now. How to find this yellow line? Okay, so to find this line, we're going to understand that in a different scenario. So let's say we are having some data points again. Let's say this, and this. On a simple scenario, we'll try to understand, and this, when you understand a simple scenario, obviously that is going to work in the complex scenario also. Okay, and let's say this, and this. We are having these 6 data points with us. So tell me, how do we draw the line that best separates the green point from the red point? Okay, how do we find the line? So again, what I'm going to do, I'm going to start by drawing a random line. I'm going to start by drawing a random line. So let's say I draw a random line, let's say something like this. Or let's take a thicker one, something like, just a second, this. We draw a random line, something like this. Okay, and now what we are going to do, we are going to calculate how bad this line is, and to find out how bad this line is, we will try to see, we will try to measure how bad the line is by finding the number of errors. Understand this. We will try to measure how bad the line is by finding the number of errors. You know, in the linear regression, we were trying to find out the distance between the data point and the line, but in this case, we will try to find out the the number of errors. That means what are the misclassification. Okay, so I can say that this is my green area. I can say that this is my green area because here the most data points are green, and here I can say that this is my red area where most of the data points are red. But there are some mistakes I can see. So we are having this as a mistake. We are having this as a mistake right now. So these two are the mistakes. So I can say that errors is equal to 2. I can say that errors, that the number of errors we are having is equal to 2. Now remember this. In the last one, we were to find the error, we were trying to find the distance between the line. But here we were not having classification. See, all the data points are blue. So we are not having some classification here. We're trying to find a value. But here we are trying to find a category. So either green category or red category. Okay. So basically here, to find how bad the line is, we will try to calculate the number of errors. So here we are having the number of error as the measure how bad the line is. Now we will try to reduce this error again. We will try to reduce this error, and to reduce this error, what I am going to do, I am going to move the line around. I am going to move the line around, and let's say this time the line comes something like this. Okay, and my error is going to be simply removed. Okay, and this error is going to become 1 because I moved the line. So my error is going to become 1 here. So let me tell you again, let's go back. So we were having this line where error was 2, and then I moved the line to this place, so my error becomes 1. Okay, because this is a data point that is lying in the wrong area, and now we have improved our model a little bit. Okay, now again we will try to move the line again. We will try to move the line around, and we will try to minimize the error as much as possible. So again I move the line, and let's say the line looks something like this time. Let me not like this, but let's say something like this. It looks something like this. So let me remove the first line before. Okay, now the line look something like this. Okay, and my error becomes what? 0. My error becomes 0. So let me tell you again. So this was my line. Now again I move the line to here, and my error becomes 0. Okay, so that is what we did. We started from the random solution, we keep moving the line, and we keep reducing the error. And if we keep doing it more and more, we are going to simply classify it and see if the error is 0. That means our data point has been classified. Okay, our data point has been classified. Now again, as I said in the last lecture, that taking tiny steps from problem to solution is called as gradient descent, or in more technical term I can say that minimizing the error is called as gradient descent. And here also we are performing gradient descent only. We are trying to minimize the error, and we will say that we are performing nothing else but gradient descent. The process of minimizing the error is gradient descent. Don't forget this statement. Okay, now in reality, in order to properly use gradient descent, it turns out that the number of errors is not we need to minimize. Yes, okay, it turns out that number of errors is not we need to minimize, but instead sometimes that captures the number of errors, and that thing is called as log loss function. Okay, minimizing the number of errors is not exactly like gradient descent, but the thing that captures the number of errors, that is called as log function, and that is what we try to reduce. Let me tell you what I'm saying. What happens is that the error function, having these kind of values is good, but we all know that but we should understand that we cannot work with these kind of discrete values going from 0 to 1, then 2. This is not possible. So in reality, what happens is that we have something called as error function. In logistic regression case, that error function is called as log loss. And what log loss does, log loss tries to penalize the misclassified data point. So let me explain you what I'm saying. So let's take the exact same example again. So let's say we are having this, and this. We are having the exact same example again. Okay, and let's again have a exact same model here. So let's say this is my random line that I'm having, which is having a lot of errors here. Now in what log loss function does, it does not calculate the number of errors, but what it does, it assign the large penalty to the misclassified point and small penalty to the correctly classified point. Okay, we are going to learn the formula later on, but that is what it does. So misclassified point is going to have a large penalty, something like this. It is going to have a large penalty. The bigger circle represents the large penalty to the misclassified point. Okay, and the small penalty to the classified point. So again, this is my green area, this is my red area. Okay, now again what we are going to do, to obtain the error, we are going to add all the error from the corresponding points, and here we obtain the large number because 2 misclassified point has a lot to the error function. That means what we are going to do, we are going to calculate the error, we are going to add all these errors here, we are going to add all these penalties here. That means something like this plus this plus this, okay, plus this plus this plus this. Okay, so this is what the total error looks like as for now. I'm not taking some value, but I'm just telling you that this is how the error looks like right now. Okay, now we are getting a very large number because of the 2 misclassified point. Now the idea is to jiggle the line around and try to minimize the error. So again, if I move the line around, so let's say the line moves from here to let's say here. Okay, now this time what happens? This time what happens that it is going to reduce the error. So it is going to reduce this error, let's say, because this has misclassified. The small penalty is going to be given to this particular point because it has been classified, and the large penalty is going to be given to the this particular point here. Large penalty is going to be given to the this particular point which is misclassified, this green point. So again, to calculate the error, we are having this plus this plus this. Okay, and the red point is going to be simply now smaller because it has been classified. Okay, and again I'm going to move the line around. Again I'm going to move the line around, and let's say the new line looks something like this. The new line looks something like this, and this time what is going to happen? My new penalty is going to be much lower for this point because it has been classified. Okay, so this time what is going to happen? I am going to have a more small error this time. This plus this. Okay. Now that is how it is doing. So we move the line around, we see that some errors decrease and some errors slightly increase, but in general we consider the sum, the total sum of the error, and we want the total sum of the error to decrease as much as possible. And as we reach the most optimal solution, we stop the algorithm, and that is where your best algorithm lies. Again, the process of minimizing this error is called as gradient descent. Okay, the process of minimizing this error is called as gradient descent. So the point of this whole process is to find the best fit line by minimizing the error function, and the process of minimizing the error function is called as gradient descent. Before I was saying minimizing the error is gradient descent, but now I am saying minimizing the error function is called as gradient descent, and that error function is called as log loss function in the logistic regression case. In the logistic regression case, that error function is called as log loss function. Log loss function. Okay, now what log loss function does? It is a very important interview question. It says that log loss function penalize the misclassified points and give large penalty to misclassified point and small penalty to classified points, and by gradient descent we try to minimize the error, and when we try to minimize the error, it is going to keep on decreasing the error until we reach the optimal solution. So minimizing the error function is called as log loss function. It's called as gradient descent. Okay, and that error function in this logistic regression case is called as log loss function here. Okay, so that is how the logistic regression works. So just for a summary, what I said, that we were having an acceptance at a university problem where we were having two criteria, tests and grades. Now based on tests and grades, we will say that whether the person should get accepted at the university or not. Now we have a student S1 which is having tests and grades. Test 9 by 10, grades 8 by 10. Obviously we are going to accept the student. S2 is having 3 by 10, 4 by 10. We are going to reject the student. S3 is having 6 by 10 and 7 by 10. We don't know whether to accept or not. So we told to the university, give me your historical data, and based on that I'll be able to predict whether the student should get accepted or not. Now in this green area that you see, that green area is representing whether the person should get accepted. Green area is representing the accepted student in the past. Red area representing the rejected student in the past. Now we draw a line that best cut the data in the two parts, and then we plot the S3 student and we find out that the person is going to accept it. Now the question is how to find this line. To find this line, we start with a random solution, we calculate the number of errors. But again, number of errors is not how we are going to do that. It was just for explanation. But in reality, the log loss way is going to be happening. What is going to happen? We are going to start with a random solution, and then we'll see what are the misclassified point. The misclassified point is going to be penalized through log loss function, and we are going to minimize the log loss function using gradient descent. And when we do that, we are going to move the line around, we keep on minimizing, again move the line, keep on minimizing, again move the line, keep on minimizing until we reach the minimum error. And when you reach the minimum error, you have your perfect solution, and that is how you find the line. Now we have more technicalities to it, like sigmoid function and all those stuff. We'll talk about that in the logistic regression section, but that is how it works. Okay, that is the most atomic level explanation. Now in the next class, we're going to understand another problem, Take it easy. If you have any question, put that in the discussion forum, and I'll meet you in the next class.